All right, good evening, everyone who have joined today. And today we are going to continue on our discussion from the previous session that was about symbolic execution. So today I'm going to discuss a bit about concolic testing and then we'll take questions regarding that. So give me a couple of minutes. I'll just share the slides and begin with that. Please let me know if the screen is visible.
Not yet, Fran.
Oh, is it?
It's not
Okay.
there. Yeah.
It'll come up, I think. Uh,
Yeah, now it is there. Yes.
yeah. So in fact, the same slide deck from which we were discussing the earlier session. But we'll skip these parts as these have been discussed in the earlier session. So instead of going through this, I'll just scroll down to the concolic testing uh, part of it. So these were the disadvantages as we discussed. Yeah. So this is concolic testing. So if you recall, we ended our discussion in the earlier class mentioning some of the disadvantages of the symbolic execution technique that we have. So it is indeed helpful in that because it is able to give us test cases depending on the conditions that we have in our program. So that is a good part. But we have seen that there are two primary disadvantages that it has. One is about satisfiability itself. So whether or not you are able to within a reasonable time, solve the predicates or the path constraints and come up with concrete values or not. So that is something that a constraint solver does. So that is one. The other disadvantage is that, for example, if you don't have the code, the entire code of the program that is under test, then in that case, of course, you cannot come up with the path constraints, and therefore we cannot proceed with symbolic execution there. So specifically regarding the second disadvantage, there is concolic testing, which tries to mitigate this particular issue, and we look at that today. So that is what it says here. Several techniques are available to alleviate the disadvantages and generate test inputs using symbolic testing. And one such technique is concolic testing, and about which we are going to discuss. So a little bit of introduction of what exactly is different between normal symbolic execution and this one. So remember that in symbolic execution, instead of having concrete values for the variables, we only had symbolic values, so to speak. So it is all like variables, and we were just collecting all the conditions, as in the path constraints together, and we tried to solve it. Right. So now the problem is that when we don't have the code, then how do we proceed? So for example, then in that case, for symbolic execution, we cannot proceed because we don't know what is going to happen next, right? Because the code is not there. So what then concolic uh, testing tries to do is that it is a combination of both concrete execution, as in the normal test case. No, we have concrete values and we just put it there and then see what the output is. So that is the other part, and the other is symbolic execution, wherein everything is a symbol. So what concolic does is that it tries to combine the best of both, and does symbolic execution path dynamically. So it will all become very clear as we move forward in today's class. But the upshot is that using concolic testing, one can also perform symbolic execution for code fragments, like for such a code which is not like completely with us. So for example, if you are trying to do a remote procedure call, somewhere else on the server. So you send a request there, you know, and a response comes back, and then you continue on the symbolic execution also, irrespective of the fact that you did not have the code for the other side. So what is it is doing is basically, wherever symbolic execution cannot be performed, we give a concrete input there, right? And depending on what the output is for that concrete input, we accordingly, create further path constraints and then continue along the same idea of symbolic execution. So that is how it is doing it dynamically, as in wherever symbols can work, we just do symbolic execution, and wherever we see that symbolic execution cannot be performed here, as in the path, we cannot generate path constraints directly, so we provide a concrete input there dynamically. So that is what the idea is. Okay, and therefore the name is basically uh, you know a combination of concrete plus symbolic. So that gives us concolic. Okay, so concolic testing is maintaining both a concrete state and a symbolic state. Remember that we talked about the sigma in the earlier discussion, in the earlier class, and the sigma was holding the state of the symbolic execution and mapping accordingly their current to the variables their current path constraints. Whatever the variables are there in the current scope of the execution, and accordingly what are their path constraints that are mapped so far. So the symbolic state was kind of a dynamic thing that kept updating as we move forward in the execution of the program. So similarly, this is the same thing, like the in concolic testing, the symbolic state is the same as in symbolic execution. However, in concolic testing we have also have another state which is a concrete state. So we are maintaining both these states simultaneously. So it is like it is also a state map. It is also a mapping. So it is also doing a mapping of the values with the variables. But in the symbolic case, it was all symbolic. However, in the concrete state, it is all going to be an actual value, as in for example, if you have an integer, then it is going to have a certain value, like for example 10, 15, 30, and so on and so forth. So yeah, concrete state is the normal notion of the state of the program, as we have been discussing, before the discussion of symbolic execution uh, came in. Okay, so the normal execution of the test cases, the state of the program that we had there, the idea of the state there is the same as the concrete state. So basically, all the values are having, all the variables are having the actual concrete values. So that is all. So we'll continue on the same example. I believe this is the same example that we were discussing, example 2. So in order to discuss this, I'll just quickly go over the source code once again to 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 be able to recapitulate uh, you know the ideas that were discussed. I think it was example 2. So yeah, this one, right? So recall that we had a twice function, and all that. So we are testing the test me function, and in that we are having two parameters, x and y respectively. Both are integers, and inside of that we are doing some kind of operation. So basically, z is getting defined as twice of y, and if the variable z is having the same value as x, then basically we go inside this block and do this another condition check. So it is x greater than y plus 10. Then if both of these conditions are satisfied, then you reach the error statement as discussed in the earlier discussion also. However, accordingly, if this is false, you will not go inside, and instead of that directly go out, come out, because after that there is nothing in this outer if block. So effectively you're going to come out of the test me function and get to main, and then finally return 0. So that is the flow, general flow. And recall that main was the entry point, so we started from here, and x and y respectively were assigned their symbolic representations, symbolic names. So that is what we did. And on those symbolic names, we are running the test me function. So this must be clear. And with this, we'll go back. So the discussion continues from there only. Example 2 is being discussed in the context of concolic execution now. So how it starts basically now, because recall that earlier we were trying to do, logically come up with the predicates, the path constraints, and then solve it and then get the concrete value. In concolic execution, however, we have to start because we are saying that we have to maintain two states, concrete and symbolic respectively. So therefore, to start with, basically it generates a random input for your variables, random concrete values, right? So for example, x and y were the two parameters that or the inputs that were there in the test me function, and accordingly, we are generating 22 and 7 for x and y, the parameters. Okay, and then we continue the execution, simultaneously, both concretely and symbolically. So it is like symbolic execution is also happening, but we are also keeping an eye on the concrete execution and the concrete state and how it is changing. Okay, so that part is also something that we are keeping a track of. That was not the case in the original symbolic execution variant of this approach. Okay, so what is happening is that we see, because this is 22 and 7. No, this is like a normal test case. Okay, so it takes the else branch because we know that it will happen. Okay, so because it is going to the else branch, okay, then therefore accordingly, because this was the concrete input, symbolic execution is generating the path constraints. X not is equal to twice of y naught, because I think I'll have to go back. So basically, if you see the first condition, I think there needs to be a way to simultaneously show both the things. Let me just duplicate, otherwise I'll have to keep scrolling. Okay, I'll come back. So I'll keep the example opened on one side so that it is easier for me to switch between the code and the discussion. All right, this was the thing. Okay, so I hope my screen is still visible. Can anyone please confirm?
Yeah, it's visible.
Yeah, sure. Thank you, Anand. So yeah, this is the discussion and this is the example under discussion. So basically, I'll keep switching back and forth so that it is easier to understand. So basically, what it's trying to say is that given that the concrete input is going to be 22 and 7 respectively for the variables x and y, the concrete execution is going to take the else part of it. So basically, okay, let's do it. So x naught is going to be 22 and y naught is, yeah, so basically twice is going to be 14, right? So twice of y naught is going to be 14, right? So therefore we can see that 22 is not equal to 14, right? In this particular case, line number 6, right? So therefore it takes the else branch. Of course the else branch is not there, but basically, what happens, we know what happens. So basically this is not true. So it is like not of this condition is true. Therefore symbolic execution is then generating accordingly the path constraints because it knew what happened, right? That is the idea. Earlier we were just going on symbolically and then generating the constraints for all cases and therefore solving it and then getting the concrete input, and then when we put that back into the function, like the solved uh, once we give that to the constraint solver, the output of the constraint solver is what we get, and then if we put that back into the function, we're going to get this take the same path. Okay, as discussed in the earlier class also. However, in this case, what is happening is that we are generating a concrete input randomly, and then we are just seeing what is happening, and according to what happened, right, we generate accordingly path constraint. So in this case, we see that it is not equal, and therefore we are generating this path constraint. I hope this part is clear. Are there any questions till now? If anyone wishes to ask, may ask, please.
Uh, Fernand, I
Yeah.
think I can wait till the end to ask a question. I have a question in mind, but
Okay.
I think you might probably want to
Yeah.
complete this.
Definitely.
Yeah,
Definitely. Okay. Thank you. Thank you so much. That is also fine.
yeah.
Okay, so yeah, accordingly, so this part is clear. So because it was not equal, it took the else part, the else branch, depending on the input, and therefore, accordingly, in the symbolic state now, we are going to have this particular path constraint with us. Okay, so we are here, the kind of the paramount difference that we can see here is that we are starting from a concrete input now in the case of concolic testing. Now what happens now accordingly, because You provided this, you saw that the program took the else part, and therefore accordingly you generated this path constraint, which was the negation, right? Then once you have that, then the nice thing happens that you can just negate that and get the other condition also, which was not there, right? So therefore the hybrid nature of this comes in here. So you generated this one randomly, you took this path, right? And therefore this path constraint came in the picture. Then you negate it, you get the other case, and then you can basically solve it. With the constraint solver, and then get the other branch also. So despite the fact that we started with random input, we are still making informed decisions as to, depending on the symbolic state, and therefore we need to maintain both the states, at the same time. And you'll see other benefits of this approach moving forward, specifically, in places where there is a remote procedure call that is happening. So what you can do there is that instead of providing a symbolic input, you can just provide a concrete input and see what is coming out. Depending on the output, then we have the path constraint, and accordingly we can negate and so on and so forth and get the other possibilities. So that is how it basically works. Now, next, the concurrent execution is going to generate this path constraint. Recall that the symbolic execution is also happening parallelly besides the concrete execution. So therefore, you're also getting this right. So this one is the path constraint when uh, I think this should be 10. No, this okay. There is this typo. It is 10 basically. X not less than equal to y not plus 10, which is the inner if condition. If you recall this one, you know. So recall that when this is false, you cannot go inside, and therefore this condition does not come into the picture. So only when this condition is true, then only you're going to check that, right? So because the concrete execution took the else part, we did not look at this condition because you go into the else part, and therefore after that nothing is there. However, when you negate that, you get this condition wherein this condition becomes true. So accordingly, you will you get another condition here, which is going to be x naught greater than y naught plus 10, and which is exactly what is here. So that is what it is generated, and then we negate it. So the reason why this is uh, there in both the cases should be apparent, because only when this is true you're going to get this condition, right? So this is like a prerequisite because this is a nested if condition. The outer if must be true there, then only you will see the next one. Therefore, in both the cases, x naught is equal to twice of y naught is given, right? That is a given thing, and we are anding it, right? So and the other condition. So what happened is that when we negated it, this one, right? This one, the earlier path constraint came in when from the concrete input. We negated it to get this. Once we got in this path, we got another condition and get this condition, right? That was the condition, and then we also negated it, similar to what happens in symbolic execution. So we negated it and got the other condition. So one condition is x naught less than equal to y naught plus 10, and accordingly we negate it, we get the other condition, which is x naught greater than y naught plus 10. Okay, and then again we solve it symbolically, right? So I mean, like, using a constraint solver. So we get 30 and 15 as one possible input, and therefore we see that the error state is reached. Okay, so basically, and of course, as I mentioned earlier also, that there are only three conditions possible then in that case. No, one condition is when this is not equal to, right? So that was there in the concrete input itself. So therefore, we need not solve it, right? Because we already had that. Given the fact that we had this concrete input to start with, and the program took this branch, took this path, therefore we didn't need not solve this one to get. I mean, like, we already have that, right? So we need not get the other concrete possible inputs for this case, right? So this is one case when x not is equal to twice of y naught. So that is one. The other case is when it is equal. So when it is equal, you get two possibilities. The inner condition is then true. I think that should be true. Less than is true. No, okay. The less than case would be false for this one because this is greater than. So if it is less than equal to y naught plus 10, then it will be false case, but it is okay. So that the other condition is this, and when you negate this one, the highlighted one, you get the other one, which is this one, which is x naught greater than y naught plus 10. I think this is the true and true case. So this is true, the earlier condition is true, you get inside, and the next if statement is also true. Therefore you reach the error state, as you can see here. So the outer if is true, the inner if is true, and therefore you reach line number 8, which is the error statement. and that is also. So therefore it says three executions, because only three path constraints are required, right? So that therefore, so you can see that we are getting all, like we are able to explore all the paths. However, uh, you know we are not doing all symbolically. We also started with a random input. However, we are still getting the same number of uh, possible path constraints in the case of concolic execution also. Okay, so this is the general idea again. So how it works is that it generates a random input, execute the program on the random input. That is the uh, normal program state, no, the concrete state. That is the normal thing. And also simultaneously collect the symbolic path constraint encountered along this execution. So what happens is that we start with a random input, we run that on the random input, and then we start collecting the symbolic path constraints. Similar to what happened in this case, given the fact that x was 22 and y was 7, the program took the else branch, and therefore we collected this path constraint because we saw what happened there. No, when you put that, we see that okay, x not is equal to y naught is the condition that is getting there, yeah, that the constraint that is getting us there, and therefore we collected that. So that is what it says in the second point. Okay. Now also steer the program execution. That is the idea. So steer the program execution along different execution path. That is, how do we do it? We use the constraint solver to infer variants of symbolic paths constraint. So we got one path constraint using the concrete state, the concrete value, depending on what happened there in the concrete state, and then we are using the constraint solver and negation to actually infer the other possibilities, right? So basically, it is negation, you know so we negate get the other possibility, and then we solve it. We how do we generate other input? Basically using the constraint solver. So when we negate, we get the other condition, we give it to the constraint solver, it gives us back the input, which will lead us to satisfy that constraint, and therefore we get the other input. And basically we repeat till all execution paths are explored or user defined coverage criteria is met. And that is what I think we mentioned, the idea of limit, or time budget, right? So either of the two. So I think in the previous class I had mentioned about the time limit, or some kind of a limit also. No, otherwise, for programs that can go on forever, like for example loops and other things that are there are so many paths. No, even if there are no loops, there is a possibility that your program has a huge number of paths, and therefore to explore all of them might not be feasible, and therefore we need to have some sort of a notion of a coverage criteria. Let's say how much I want to cover, or a time limit, and that possibly if that expires, we stop it, right? So either of the two could happen, right? Three, in fact. So one possibility is that you are able to explore all the paths, so that is one. The other is that you are meeting your own coverage criteria, whatever you desired, or the time budget expires. So three possibilities are given here. Now this is the other example for this one, and I think it will make it more clear. So let us go through this also. This must be a good one. So it says there is this function h that is taking yeah, this function that is taking two integers, x and y. So it basically says that if x not is equal to y and fx is equal to x plus 10, then you abort. So keep in mind that the abort statement or the error statement is, like, in this context, basically mean the same thing, as in the statement which we want to reach. Herein it is, I think, not made explicit that we are willing to reach the abort statement, but that is basically what our intention is. Okay. So in this program, the idea is to reach this abort x statement. Okay, and then we return. So again, the same idea applies. Uh, we have to reach the defective function h is difficult using a randomly generated test input. Yeah, exactly, because only based on the random input it is difficult to figure out which one will basically lead you to this particular statement, right? So therefore we can use the concolic testing idea here too. So it says we generate one input randomly. Okay, that is fine. Now that is the idea of, in some sense, search also, no? So we started at some point, then we knew where we have to go. So we are in some sense trying to optimize now based on that. depending on what the trajectory is, right? In some sense, we are trying to drive again the program to our intended path. So for example, if I want to reach a specific portion of the program, I start with a random input, that is okay, but that might lead me somewhere else. Okay, I don't want to go there, but then that is a good starting point, because then again I can see what corrections I need to make in my path constraint so that I reach my correct path. Okay, so it is still helpful to have a random input that can guide us towards that, right? So that is what. So basically, yeah, so that is what. So it generates 26 and 34, right? Then that is what is formed using concolic execution, as in the concrete execution. X not is equal to y naught, that's okay, and the other one. Then we uh, calculate the other path constraint, negating the last one. So basically we negate it, right? This one is true still, we negate this one. So twice of, I think there are a lot of typos here. I think we'll have to mention this. This should be twice of x naught not is equal to x naught plus 10, right? This is the condition, I think. I think the two got missed out here somehow. Sorry about that. Yeah, so this is twice of x naught not is equal to. So it was not is equal to x naught plus 10, and therefore we are negating it, getting the other case, and then we have this one. It leads to the else statement. So basically, it is some sort of a informed kind of uh, you know procedure wherein we are trying to understand what kind of input can drive us towards our intended path, because that is very helpful in testing, right? Again, going back to the idea of reachability and infection and propagation and all that, the very first thing when you're trying to when we're trying to come up with a good test case design is that you have to have something which reaches the the error, portion of the error. Otherwise, how do you test, right? And we have seen that inside of the program there's so many uh, you know so many state changes that are happening. It is very difficult to predict what would be the output, the initial output, because it is getting transformed, no, along the path. So how do we know that we are going to reach wherever we want to reach, right? Because the initial input might be entirely different, that you're giving there inside, and inside of that it might get into a different uh, it gets transformed into a different kind of formulation, and basically the path constraints differ across different things. Recall the idea of I mentioned about the fact that one test path, though it might seem close, like for example 26 and 34 is there. How do we measure like where it leads us? Because even a single change, let's say I might possibly make it from 26 to 25, and it might lead to an entirely different path in the program, depending on what the code is, right? It can be anything, we don't know. So there is no notion of how close two inputs are, and therefore it is difficult to do it by hand and manually. Therefore it is saying that uh, it is difficult to reach directly using a randomly generated input. How do we test, right? And even, okay, you might be able to do it like by hand also, by seeing the conditions, but how do we then automate the process? So that is what Concolic is helping us. I think it was all
Afnan,
very short about this. Yeah, so this was the last one.
hi
We'll
Afnan.
go, yeah, go on please, Anand.
Yeah, can you go to the code for this?
Yes, sure.
Uh,
Oh no, this one is it,
Not this one. Yeah,
yeah, this one, yeah.
this one. Okay, so this is x is not equal to y. Okay, so what about x is equal to y? Where
Oh,
is that case?
yeah, that is correct. But we were trying to reach this portion, no, because therefore I think we did not consider this. But yeah, if your intention is to visit all the execution paths, then you negate this one also and get that.
Yeah, because that one was the first thing to do, even before the reversing the other one.
Makes sense. This one, right?
Yeah.
Yeah, yeah. This one comes up first actually because of that fact that you go inside and then you basically negate. So I think this is not mentioned here, because if you negate this one, you know, you're not going anywhere after that. Nothing is there, right? So if you skip this branch, you're basically going to return 0, and that doesn't help us. So I think that is why it is not discussed. But yeah, I think the
Yeah.
mechanical procedure by which we do it is that you negate everything and basically get the other case also. So
Okay. Okay. So can I ask the question I had? I wanted to
Definitely,
ask.
because this is the last
Okay, so
slide. Yeah,
I think can we go back two slides in
yeah,
this?
definitely. Code itself, is it? Yeah.
Not this one. I think
Okay.
the last example you showed.
Oh, the last example, is it? This one?
Yeah, right. So in this one, let's assume that the function twice. I mean,
Hmm.
we currently know that what the twice is doing because we have the code for that, right? So
Definitely. Yeah.
when we actually write our symbolic execution and try to I mean, when we are executing them parallelly, the concrete and symbolic, then we know that we have to take like 2x0,
Yeah.
sorry,
Like two,
2y0.
two, one. Yeah, exactly.
But
This
let's
one.
say we don't know what is the code for that.
Yeah, this one, right?
Yeah. So what are we going to do?
Yeah. So, but basically, what are we going to do is that we'll provide, instead of providing why not here, we'll give something. Let's say I give 4 or whatever, right? I give
Mhm.
4. So Z will be having something. And recall that the concrete state is entirely the concrete state is entirely concrete, right? And the symbolic state is entirely symbolic. So in the concrete state, even your x is going to be concrete only, right? It is not going to be right. It is not going to be x naught. It is going to be some value, right? Because we are starting randomly. Right. Now we see what happens. So you are saying that twice is not there, that's okay. So I provide in some value, let's say 10 here. Right. And x is also something depending on what x is. Let's say x is 20 for the sake of this argument. And then what happens? So you go to twice of 10, you don't know what it is doing, but assuming that you get return, because return you will get, right? So you get 20 out of this. So z is assigned 20, and you come here, so it is 20 is equal to 20. You see now that is what happened. Even though I did not have knowledge of this particular thing, what it is doing, I got 20 out of that. And I'm seeing that I'm going inside because this 20 is equal to 20, given that x was 20 randomly, right? And then I can negate and go forward, right? So there, we
Uh,
need not.
yeah, but the seventh line, how do you reverse that? So we
Mhm.
assume that that y is two y, right? So y is actually two y.
Mhm.
So we took a concolic there as
Mhm.
2y and we actually reverse that.
Definitely.
So right, so will we be able to do that is my question. So since we don't know if it is 2y, because if you go down one slide, if you go down one slide,
Yeah, here it is.
yeah, so the um
Line
okay, so
7.
I think line 7, yeah, so line 7 says x0 is equal to 2y0
Yeah, this
and
is this.
yeah, and okay, I think this is a mistake, is it? Okay.
Which one?
Um, okay, I'm getting a little confused now.
No, no, it's okay.
Uh,
Yeah, you can take
okay,
your time.
maybe I will frame the question properly in my mind. I will
Definitely,
pick
I
that up in
understand,
Discord.
and I
Yeah.
somewhat understand what your, what your question is exactly. The essence of your question, I kind of get it. So, basically, you're trying to say that how do we then negate if we don't know what the condition is going to be, right? That is what
Yes.
you're
Yes.
saying. So
Yeah.
what happens now? So what happens? Yeah, I get it. So here in the symbolic state, let's see what happens. Let's try to imagine. So what happens? So y is getting twice of y, right? What happens because of twice? Nothing except the fact that it is y is getting transformed to twice of y naught. No? That is what is happening, right? As a result of this twice, right?
Mhm. Mm.
And to y nothing happens. Y is, I mean, like x and y are independent, right? I mean, in the concrete state, it is going to be concrete only. In the in the symbolic state, it is going to be symbolic. So the confusion is there only, like in the case of z, right? So even if we don't know the formula, right? Because our intention is not to really know what the formula is doing, right? Our intention is to only check the conditions, right? So the condition is only asking about whether z is equal to x or not, irrespective of what x is going to be. Sorry, what z is going to be internally. The formula for that.
But unless we know the what is happening inside the device, how do we submit it to the solver? How does the solver do
Yeah,
the?
exactly. That is what I'm saying. So you need not have that. So for example, let's say you know here that x naught is equal to x naught is equal to twice of y naught is one condition. Or for example, you know this fact. This fact is there that twice of y naught. You know that, right? For example. So what
Okay.
is happening if you don't know twice? it is going to be replaced by z, right? Whatever z is, because that is what it is. I mean, there is some z we know that is coming out of twice. What twice is doing, because 2 is insignificant here, no, as regards the condition itself. How is 2
Yeah.
making a difference here? If even if 2 is not there, I'm just saying x naught is equal to z naught, let's say z naught, right? And then I'm negating and getting x naught naught is equal to z naught. That is all there is to it. Whether I write it as the whole formula or only one variable, it doesn't matter, right? Because my condition is going to be dependent on that only, not on the actual formula. Because the formula comes in the picture only in the concrete state, right? Even if we have 2 here, you're only having y naught. No, y naught itself is a variable, so it doesn't make a difference whether we have a 2 here or not. I hope you're trying to,
Yeah,
uh,
I'm getting it, but I have
y-
to rework on this to get a
yeah, yeah.
good
Eh,
understanding. Yeah.
yeah,
Okay,
definitely,
I
definitely. So
get it.
yeah, this is in fact a very valid question, and an interesting one, because we see that we don't have the whole knowledge, like the whole information. Then how do we infer the path constraint is what your question is. So that is a valid question. But then again, it all boils down to the conditions. If my concrete variables are able to give me one condition, because my intention is only to drive the program, right? And that by that by modifying the condition, the output of the conditions. So basically, if I were getting true somewhere, I want to make it false so that I get the other branch. If I were getting false somewhere, I want to switch it so that I get true, and if I get true, I get the other part. Because there are only two possibilities, right? Either is something is going to be true, because that is the idea in Boolean, right? So it is only going to be true and false. So if you are getting true somehow, I don't care about the internal formula, what it is. If I'm getting out of the concrete execution true, right, then I basically negate it, get the other case also, and then solve it, right? So
Yeah.
I
Can I extend this problem? I mean, since we have already learned the black box thing,
Mhm.
can I extend this? For example, if the instead of the twice function, let's say it's a very complicated function which
Mhm.
has a couple of ifs and a few for, and there is a
Yeah.
nested loops and all that. So let's say
Okay.
it's a very complicated function. Are we going to use, so for this concrete purpose, are we going to use employ any black box techniques to test?
Yeah. It might be useful there too, because you're saying black box, which means that we don't have the access to the source code again.
Yeah,
So we have to have some kind of a concrete input that goes in, and finally we get out something, right? Because the idea of a module or a whatever function is that it is going to give you back something. Even if it is an API call, it will have a return value, right? It cannot be nothing, right? Something must come out of that. So whatever comes out, we accordingly, because our intention is, see, our purview is within the function that we are testing. Now there are dependencies for the function that is under test, that the function is dependent on, and for the code for those dependencies is something that we don't know, right? But that is not of our concern whether we know that code or not, the external, so to speak, code, or the black box code, as you mentioned. So as long as I am able to drive my function towards the different execution paths, that would be fine. So now I give concrete inputs where for the portion wherein I don't know the whole code. I give in concrete values. Whatever comes in, I then negate it. I get the other case, right? So I
yeah.
mean, basically, that's what we try to do.
Okay. So our purview is actually limited only to white box testing for the function which has code.
Yeah, definitely, definitely.
Right.
And there,
Okay.
it might have dependencies, uh, which you don't have a complete view of, and therefore we are getting this disadvantage in the symbolic execution, and that is what concolic is trying to
Yeah.
alleviate.
Okay. Yes.
Okay,
Okay.
so
Thank you.
yeah, yeah, sure. Thank you so much. And I think, yeah, so it was rather a short discussion, because about concolic testing, most of it was actually, because it is all building upon the idea of symbolic testing itself. It is nothing new, because the concrete testing is something that we all do. It's a general thing. So we'll provide test input, see what the output is, match it with the expected output and all that. But how can we use it to do, maybe maybe get better test cases, maybe maybe a little more, get a little more informed because of whatever we are getting. So I know, right, I mean, this is like we can understand it, intuitively also. So, for example, if I provide in something, let's say I'm going to test something, right? So, what do I do? I will provide something. I see what are my conditions. So I see, okay, if I provide this and this value, so and so value. So what is happening is that this program is going to this part, and then it is coming out from there, and it is running the loop this many times, and then it's coming out, and then it's doing so and so. Okay, and this is the final output. That is how it went. So if I know that my path, my execution path for this test case input was something like this, then the idea is to I'll also try the same thing. No, if I'm doing it by hand, I try doing it something. So I'll try to vary it, right? So because it doesn't make sense to keep testing the same execution path again and again and again, because we know that under this, like for example, this execution path is fine. There is no issue in that. My logic is completely fine. So if I'm providing negative inputs, then I know that my program is handling that very well. If I need not test that, then why do I provide negative inputs? Now go to positive inputs and test that. Right, so that is where the partitioning also comes in, right? So there is something more to it in the black box version of it. Basically, input space partitioning, and that is completely black box. So that doesn't even bother about what the code is. So you basically, as a tester, if you want to test something from outside black box testing, then how do you ensure that whatever your inputs are in your test cases, how do you partition it? Like how do you test? How do we know, right? Because if you think about it like that, maybe for us it is somewhat easier to understand because we have that kind of a background and we've been discussing that, so it might be a little easier to understand it for us. But think about it. So I mean, it is very difficult in black box testing to understand what inputs to provide first of all. Right, because we don't have the code. So if you have the code, you know what is happening, so you might try varying it a little bit and then seeing, okay, no, I know that, okay, if I provide this, then it is going to return false here, and therefore it will go into this particular branch and then continue like this. So if I do make a little bit of change here, then in that case I might change the trajectory of the program, and it'll end up taking this path, and therefore it will give me that output. So I can kind of make such inferences if I have the knowledge. Now if I don't have the code, I don't know anything what is happening, right? Then in that case, how do we partition? We don't know, right? What do we provide? So I mean, do we need to test for 2 and 3 separately, or what? I mean, like, speaking of integers, we have, right? So there has to be a way by which we do all these things, and that is what ISP, or input space partitioning, is concerned about. So I think that might be a discussion for the next live session. Otherwise, if you have any questions that you would like to ask specifically, we can take that up in this session also. Okay, so the last slide was remaining a few words about the solver, because that is like the heart of the idea. So it basically, because until unless you can solve whatever path constraints you're getting, you're not getting going to get the concrete values, and therefore you cannot. Because at the end of the day, the actual testing, to me, it seems as if it is happening on the concrete input, after all, because even if you have that path constraints and everything, it is only to drive the program. Once you solve it, no, you're going to provide that input actually and see what the expected output was and what is the actual output, and therefore you compare and go back to the test cases again. So that is how we do it. So I mean, without constraint solvers, it cannot happen, of course. So therefore, there's a bit of discussion about this. So it says it can solve complicated nonlinear functions also, and it basically, these days constraint solvers are very good. So many years of research spanning over several papers have extended these techniques to handle pointers, files, multi-threaded programs, dynamic data structures, etc. So many things are there. Some of the tools are mentioned here for the programming languages respectively. So for example, there is this thing called CUT, or Qt for C, and UIUC, and JQt for Java. uh, and okay, I think this must be at, I don't know, UIUC stands for, it must be an acronym for the place at which it got developed, maybe, possibly, not sure about this. And there is this PX, or PEX for .NET, for the .NET family of languages. PEX is there. These are all constraint solvers. And Sage is another tool from Microsoft. Other companies have also developed, like for example, NASA have their tools, and IBM, Fujitsu, and etc. Because why constraint solver again are somewhat studied across various applications, because of the fact that their use cases are very general. So it is not that you're going to use constraint solvers only in software testing. So these are general solvers in some sense, right? Because you have this everywhere, right? So in operations research, in maybe airlines and traffic planning and stuff of that sort, right? And networks and other such things. So you get constraints everywhere, even finance, right? So if we are able to improve the constraint solvers generally for a wide variety of applications, but again, there cannot be, at least according to the state of the art currently, there cannot be general constraint solvers which are good at everything, because depending on the application also, there are some heuristics that are applicable to a specific applications. So for example, you cannot have a constraint solver that is good at everything. So therefore there are various implementations. So but in general also, if you are trying to optimize constraint solvers, or even for a particular application, that more often than not, that ends up being used at different applications also. So for example, if you are able to come up with a good constraint solver, then it need not be used for testing only, right? It can be used somewhere else, and that is still a very useful thing, right? So therefore these various implementations come in, and all have their own advantages and disadvantages, and some are specialized for specific use cases, while others may be more general. There is one more tool for which I'm not seeing the name here. I'm also not able to recall. I'll mention that. I think it was starts with Z or something. I don't know. It is from Microsoft again, I believe. That is also a
Yeah, I
solver.
read something called Z3 somewhere. I don't.
Z3. Yeah. That one.
I heard about it somewhere. I think in the lecture only, but I don't recollect where I
Yeah.
saw it.
Exactly. So that okay, maybe Professor Meenakshi might have mentioned it like on in the lecture. It was mentioned. So Z3 is again like Sage. Z3 is again from Microsoft, and that is also one of the most popular constraint solvers, and that happens to be open source also, if I recall correctly. So there are implementations on top of Z3, which are then specialized for various specific use cases. So that is one. So this is like a very active area of research, and it again goes back to it has a lot of overlap. So if you go back, you see again it kind of connects to the SAT problem, the satisfiability problem, and then the satisfiability problem in some sort is like it's like the core of the complexity theory, the P versus NP and all that. So which are of the central interest in computer science, even since a very long time, not today. So there have been a lot of research, in these areas. So again, so our discussion was only in the purview of software testing, and we can see even concolic execution can prove useful uh, in such cases, right? So and that is also called Dart. So that is one point that I missed. Concolic testing is also called Dart. Directed automated random testing is because again, so you can infer some things from the name also now. You can say it is random because we start with a random input, right? And then we direct it, right? I mean, we try to direct it to a specific path, and that is automated, right? So that is where the name comes from. So it is directed automated random testing or concolic. So concolic is basically concrete plus symbolic. So that is all. I think that is all that was there in the slides to cover. If any one of you have any questions, please feel free to ask me. Just answer them.
So how do you calculate the number of nodes in the symbolic execution tree?
Okay, all right. So that is something that has been there for a long time. So actually, it varies. Whoever asked, Bhavya, is it?
Yeah.
Did you ask? Okay. So actually, it varies. No, there are different conventions that people have come up with, and I have examples. I might be able to present it maybe in this session. If I don't think I'll have to look up actually. I have that example, but I have to look up. So maybe in the next live session, or maybe I'll put that on Discord. So you'll
Yeah,
see
I've
there are.
asked it on Discourse. It's
Hmm.
been a couple of days, I think. Yeah.
Yeah, definitely. So yeah, we will answer that. We'll check that and then answer.
All
So
right.
basically, there are variants of uh, drawing the symbolic execution tree, and due to that, due to the differences, mostly because of whether you are combining or not. Again, in control flow graphs also we've seen that, no, because if you combine the nodes you get less number of nodes,
Yeah.
but the structure remains the same. So similarly there are other conventions by which people draw the symbolic execution, and particularly the number of nodes, it varies, right? So other things might not vary, but the number of nodes may vary, and therefore that ambiguity kind of arises. So wherever we ask that, no, either we'll provide a convention to follow, or maybe we'll avoid that. So I mean, either of them.
It's given in the practice assignment 7, and there's not much given in terms of conventions to be followed.
Yeah.
That was
So
where my concern stems from.
exactly, we can understand. So no, we will try to avoid that ambiguity. In fact, we had discussed this with professor also. So she mentioned that again the same thing, that both I mean, we described two examples wherein there were two different symbolic execution trees having different number of nodes.
Yeah.
So she also mentioned that both are valid ways of representing or drawing the symbolic execution tree. So the number of nodes can vary. So therefore we kind of decided that questions pertaining to specifically to the number of nodes in the symbolic execution tree, exactly the number of nodes, might be avoided, will be avoided, in fact, more, almost always, except possibly when the symbolic execution tree itself is there, or a convention is there. So at least in the exams and the quizzes, we'll try to avoid that. Okay.
All right. Got it. Thank you.
So that might not be a problem. I think in the previous back then, I think one of the questions were there in the quizzes, wherein multiple answers were provided. So what we did, I think we provided, we actually mentioned both answers as correct. It's like, whether it is going to be 8 or 7, something like that, 4 or 5.
Right.
It mostly one or two nodes that vary. So basically we try to make both the answers correct, maybe, or altogether avoid asking
All
uh,
right. Got it.
such questions. So might be okay then in that case.
All right. Thank you.
Thank you so much, Mavya. Anyone else? Any other questions, or shall we close for today? Uh, what was your question, Anand? I missed out that on the discourse form you mentioned. No, there is this question that you had put up.
For the week 7,
Yeah,
uh, I think this was one of the what Bhavya just raised is one of them.
symbolic. Okay,
Yeah,
execution tree.
the
Yeah.
number of nodes.
Hmm.
Uh, I don't recollect the others. Maybe I
Okay. Yeah.
can.
Hmm.
Yeah, I don't think there is anything I cannot live with. But as of now, it's fine.
All right. All right. No, no. I'll go through that.
Okay.
And answer that. So it so happened that I was like out for a couple of days, and therefore, uh, yeah, somehow it's not able to answer, but I'll do that. Okay.